So, this is going to be the first lecture on the representation theory of finite groups. I'm going to be using the book by Steinberg. This book is great. Uh, it takes, I think, the simplest approach to the subject, which is through the theory of characters, which is really nothing more than the trace operator. So there are sort of higher level approaches to this topic uh, through the use of things like modules. We don't really need these on a first approach, so we're not going to bother with those, and Steinberg doesn't either. So we're going to be sticking to finite groups. If we move to infinite or continuous groups, then it's possible that we'll need to encounter these higher level topics. Okay. So without further ado, let's talk about sets. So first thing I have to tell you is what I mean by a set. And I'm going to give you sort of an informal definition. I'm going to assume that we all know what a thing is. So, and we'll call a set a collection of things which we are going to call elements. So again, I won't define what a thing is. I won't define what an element is, or I won't define what a collection means, whatnot. Um, I'll take all these things for granted just because we have to start somewhere, and these words are all very intuitive. So as an example, we take the set of all elements in the alphabet. So our notation for a set is a pair of curly braces with a list of all of the elements in between them. We can also take the set of natural numbers. This is an infinite set. We usually denote it the capital N. We also have a combination of these things. The things in the set don't have to be all the same kind. And we could even have words, mom, dad, brother, sister. It doesn't really matter. Okay, so a subset X of a set Y is a set for which if X is an element of X, that implies that X is also an element of Y. So every element of X is also an element of Y. So this is the only structure that a set really has. It's just a list of things. There's no addition defined, there's no multiplication, etc. Still, it might be useful to know how these things are classified. So to this end, let's define a notion of a map between sets. So a map this definition is sort of informal as well. It's just an assignment. Is an assignment of an element x in the set x to an element f of x in the set y. For example, if x is the set 1, 2, 3, and y is the set ABC, well, one map we could define is given by setting f of 1 equal to A, f of 2 equal to B, and f of 3 equal to C. This is not the only map we can define between these two sets. We could easily have set, for example, everything equal to A. We could have set f of 1 to A, f of 2 to C, f of 3 to B, and so on. There are so many maps we could have defined between these two sets. But I've glossed over some details here. I never really defined what was meant by this equal sign here, here, here. What does it mean for f of 1 to be equal to to A? So to understand this, we really need to define what's called a relation. Binary relation. We'll call it R on a set X is a set of ordered pairs of elements of X. What does that mean? It means R is a subset of the set of ordered pairs. So when this is the case, we write, so if AB is in R, we write A, R, B, and we say that A is related to B. Okay, so here's an example. We could have X be 1, 2, 3, 4, so on. This is the natural numbers. And we could have R be equal to the pairs 1, 1, 2, 4, 3, 9, and so on. So what's the rule here? Well, what we're doing is we're taking an integer, a positive integer, more specifically, n, and we're saying that n is related to its square. So notice that for one, if A is related to B, it doesn't necessarily mean that B is related to A. Okay. Well, as it turns out, we want that property as well as some others. So here's another definition. We want a very particular type of binary relation. We're going to call this one tilde. So binary relation tilde on a set X is called an equivalence relation. if and only if it satisfies the following. So one, we need x to be related to x for all x in the set x. This is called reflexivity. Two, if x is related to y, then we need y to be related to x. This is called symmetry. And this must be true for all xy in our set x. And then three, if x is related to y and y is related to z, then we need x to be related to z. So this needs to hold for all x, y, z in our set. And this is called transitivity. Okay. So there's a very special set that we're going to need to consider, which is the following set. So given an element x in our set x, the set denoted with these square brackets around x is the set of all y in x such that y is related to x. This is called the equivalence class of x. So it's the set of all things which are related to x with respect to this equivalence relation. In fact, we're not going to use the word related anymore. We're going to say equivalent. So here's an example. We could take the set Q of rational numbers with the usual equal sign. So in this case, we have that 1/2, for example, is equal to 2/4. And this is equal to 4/8. Well, it's also equal to 8/16, and so on. So what's the equivalence class of 1/2? Well, it's just all of the fractions which reduce to 1/2. Okay, so we could write that out in exact detail, but we're not that invested in this example, so we won't do that. Okay, so this notion of an equivalence relation is really exactly what we need to make sense of that notion of equivalence between f of 1 and a. And moreover, it's exactly what we need to talk about when two sets are equivalent to each other as sets. But the trouble now is, how do we define this equivalence relation in order to capture the notion of when two sets are equivalent? Well, here's a naive approach. We could say that given two sets x, y. X is equal to y when, let me use a different letter other than x. Let's say A is in x if and only if A is in y. Okay, so this is indeed a perfectly good, equivalence relation. We could check that. So we have reflexivity, because A is certainly an x if and only if A is an x. So this equal sign is certainly reflexive. And if x is equal to y, then A is in x if and only if A is in y. But this is exactly the same thing as saying that A is in y if and only if A is in x. And that's the same thing as saying that y is equal to x. And so we have symmetry as well. Now, if x is equal to y and y is equal to z, then that tells us that A is in x if and only if A is in y, and A is in y if and only if A is in z. And it follows that A is in x if and only if A is in z. And that tells us that x is equivalent to z. Okay, so we have our reflexivity. So this tells us that x is equal to x. We have our symmetry, and we have our transitivity. So that proves that this equality is indeed an equivalence relation. Okay, well, it turns out that this approach really leaves much to be desired. So suppose that you had 3 coins. Let's just draw 3 coins here. And let's say that you labeled them 1, 2, and 3. Well, you could just as well have labeled the 3 coins A, B, and C. And so what we would like is to be able to describe these sets as being somehow equivalent to each other. The equality that we've derived so far doesn't accomplish that, because, well, these sets are entirely distinct, right? They have different symbols in them. Well, what we could do is we could notice that these 2 sets are just a relabeling of each other. So we could construct a map that takes 1 to A, 2 to B, 3 to C. And we could say, okay, what we could do is we could define 2 sets to be equivalent if there's a map from one to the other. So here's our naive approach. Rather, our less naive approach. So we're going to have a working definition here. Let's say that 2 sets x, y are equivalent if there is a map f from x to y. So actually, it turns out that this is a very bad definition. So you can always define a map between 2 non-empty sets. So this definition is much too weak. It implies that all sets are somehow equivalent to each other. So here's an example that illustrates why we really don't like this definition. You have x equal to 1, 2, 3, and you have y equal to a. Well, you can construct a map F as follows. Let's list out the domain and the range. Well, the only option is to send everything to A. So with our working definition, this implies that the labeling of the coins with 1, 2, 3 is equivalent to just labeling them all A, and this is not at all what we want. Right? This makes no intuitive sense. This is not what we're looking for. Let me give you another definition. Map F from X to Y is called injective, or 1 to 1 if A is equal to B whenever f of A is equal to f of B. So in other words, if f of A is equal to f of B, then that implies that A is equal to B. Okay, so here's an example. Let's take the map F from the set 1, 2, 3 to the set ABC, and we'll define it first by sending 1 to A, 2 to A, and 3 to C. This is a perfectly good map, but it's not injective. Why? Well, because f of 1 is equal to A, which is equal to f of 2, but 1 is not equal to 2. So injectivity fails. Here's a map that is injective. It takes 1 to A, 2 to B, 3 to C. This is perfectly injective. Every element on the left is mapped to an element on the right, and no two elements on the left are mapped to the same element on the right. So this is indeed injective. Okay. So again, injectivity says that no two elements of the domain get mapped to the same element in the range. So requiring our map to be injective would therefore get rid of that example where 1, 2, and 3 all get mapped to A. So let's adjust our working definition. We'll say that two sets X, Y are equivalent if and only if there is an injective map F from X to Y. Well, it turns out that this still isn't quite what we want. It solved the problem from before, where 1, 2, and 3 were all mapped to A, but there's still yet another issue here. Take, for example, the map between the two sets 1, 2, 3 and A, B, C, D. You can map 1 to A, 2 to B, and 3 to C, but notice that nothing gets mapped to D. We could also take 1, 2, 3 to ABC by going straight across. So if this notion that we're defining is meant to be an equivalence relation, then, well, this guy implies that 1, 2, 3 is somehow equivalent. I'll use this equal sign with a tilde above to distinguish it from the equal sign we derived earlier. So this is somehow equivalent to A, B, C, D. But over here, this guy is telling us that 1, 2, 3 is somehow equivalent to ABC. Ooh, that's supposed to be a tilde. But we know that an equivalence relation is transitive, which means that if this is equivalent to that, and that is equivalent to this, then the end pieces must be equivalent as well. And of course, this defies our intuition. Okay? This is not really what we want either. So in fact, this definition will also imply, for example, that 1 is equivalent to the set 1, 2, is equivalent to the set 1, 2, 3, and so on. Okay. So we still don't quite have what we want. We don't need all these extra elements in our set after the relabeling. Okay. We want to somehow get rid of those. Okay. So we need the following definition. A map F from X to Y is called surjective if for every Y in Y there exists an X in the set X such that f of X is equal to Y. Okay, so in other words, every element of the range is hit by the function f. So here's some examples. So that example from before, where 1, 2, 3 got mapped to A, B, C, D, like so. This is not surjective. Why not? Because there's no X for which f of X is mapped to D. Okay, so here's another example. 1, 2, 3, A, B, C. We could map 1 to A, 2 to B, and 3 also to B. So this is also not surjective. But it also isn't injective. So it's not surjective because C is not hit by the function. Right? Nothing is mapped to C. And it's not injective because f of 2 is equal to f of 3, but 2 and 3 are not considered equal. So the map before actually is injective. And finally, let's take the map that just goes straight across, like so. This is surjective. And it also is injective. It's surjective because everything on the right gets hit by the function. So there's always a value in the domain which gets mapped to the value on the right. And no two values on the left get mapped to the same thing on the right. Okay. So there is a name for a map which is both surjective and injective, called a bijection. A map that is both injective and surjective is called bijective. or if you like, a bijection. Okay, so that leads us to the following definition for when two sets should be considered equivalent. We'll say that two sets x, y are equivalent, or just to distinguish the notion of equivalence from the equal sign that we derived earlier, we'll get rid of this word equivalent and we'll say isomorphic. So we'll say two sets xy are isomorphic if there is a bijection f from x to y. In this case, we write x isomorphic to y. Okay, so this definition finally really captures the notion of equivalence that we set out to define. It captures that two sets are considered equivalent or isomorphic, as we're putting it, if they're just a relabeling of each other. So in fact, this notion of equivalence that we defined is indeed an equivalence relation. So to see this, we're going to need a couple of facts. Let me go ahead and, well, first I need to define what an inverse is for you. So if f is a map from x to y, and g is a map from y to x, then g is called a left or right inverse f if and only if g composed with f is the identity map on x. Or for the case of a right inverse, it would go the other way. Because f composed with g is the identity on y. So a left and right inverse is just called an inverse. Some people call this a two-sided inverse, but we're fine with just inverse. So I should notice what I should note what these identity maps are. So this identity map on x, what this means is a map from x to itself. And the way it's defined is if you are given an element x, it just outputs that same element. So it's defined similarly on y. Okay, so we need a couple of results to show that this thing we defined is indeed an equivalence relation. So here is a lemma. Map f from x to y is a bijection if and only if it is invertible. Invertible just means that it has an inverse. So here's the proof. go this direction first. So we're going to assume F is a bijection. And what we want to show is that it's also invertible. So we can construct some function g for which f composed with g is the identity and g composed with f is the identity. Okay, well, let y be in the range. Since f is surjective, f is surjective because it's bijective. That means it's both injective and surjective. So since f is surjective, there exists an x in the set x such that f of x is equal to y. So we want to build this inverse of f. So how do we do that? Well, what we do is we define g from y to x by g of y equal to x. So which x are we assigning to an arbitrary y? Well, the one that we know exists by surjectivity. So you could argue that this function is not well defined, right? Because what if two things in x get mapped to the same thing on, the same value y? But that can't happen because f is injective, right? And so g is indeed going to be well defined. Okay, so then f of g applied to y is equal to f of g of y. And well, g of y is just f of x. Sorry, g of y is just x. And so we're left with f of x, which is in fact y. And so this implies that f of g is just the identity on the set y. So similarly, we can show that g of f of x, well, this is just going to be g of f of x. F of x is y, so this is g of y, but g of y is x. And so this implies that g of f is the identity on x. Okay. So what does that mean? That means that f is invertible, which is what we wanted to show. What's its inverse? Well, it's this function g that we constructed. Okay, now for the reverse direction, suppose that f is invertible. Well, what does that mean? That means that there is a map g from y to x such that f of g is the identity on y and g of f is the identity on x. Okay, so now what we want to do is we want to show that f is also a bijection. So how do we know that it's injective? Well, if f of x1 is equal to f of x2, we want to show that x1 is equal to x2 because that implies injectivity. Well, then we can apply f to both sides. That means that g of f of x1 is equal to g of f of x2. So I should say here for some x1, x2, and the set x. Okay. But g of f of x1. Well, g of f is just the identity function. What does the identity function do? It just takes x1 to itself. And same thing on the right-hand side. So this implies that x1 is equal to x2. And therefore, f is injective. Okay, so how do we get surjectivity? Well, let's just take some arbitrary y in the set y. What we have to do is we have to find some element of x which gets mapped to y. Well, I know that if y is in the set y, that means that g of y, which is the inverse of f, is in x, right? Because g is a map from y to x. Okay. And I know that f of g of y is equal to y, because f and g are inverses. Okay, well, I just found an element in x which gets mapped to y. And this holds for any y. So f is surjective. Now, f is both injective and surjective, so f is a bijection. And that completes our proof. So we know now that a function is bijective if and only if it's invertible. And that the intuition here is pretty clear. If you have a set of, let's just take a finite number of things. Well, the only way I'm able to invert a map from that finite number of things to another finite number of things is if each element on the left is mapped to one and only one element on the right. Okay, so just a quick note. We usually denote the inverse of a map f from x to y by f inverse from y to x. Okay, so this f with the -1 in the exponent. Okay, so we need one more lemma. And it turns out it's pretty easy to prove using lemma 1. So if f from x to y and g from y to z are bijections, then h, which is defined to be g of f from x to z, is also a bijection. So the composition of two bijective maps is also bijective. Well, here's the proof. Since f and g are bijective, lemma 1 says they are invertible. So we'll call their inverses, we'll call the inverses f to the -1 and g to the -1. Then the map, let's get this right, it should be f inverse composed with g inverse is an inverse for h equals g of f. I say an inverse, but really it's the inverse because the inverse of a map is is unique. Okay, so to see that this is true, well, we just compose F inverse of G inverse on the left with G of F. And how does function composition work? Well, it's associative. We can just move this parenthesis around. So G inverse of G, this is the identity on Y. And so we're left with F inverse of the identity. The identity does nothing. So this is just F inverse of F, which is the identity on X. And similarly, G of F composed with F inverse of G inverse is equal to G of F inverse of G inverse. This is the identity on X. The identity on X does nothing. So we're left with G of G inverse. And this is the identity on Y. Okay. So what does this tell me? This tells me, my apologies, I need to up. This tells me that F inverse of G inverse is the inverse of, let's see, this is G of F. But then that implies that G of F is a bijection. This is by lemma 1. So lemma 1 tells us that a map is bijective if and only if it's invertible. We just found an inverse, and therefore the map is bijective. And that completes the proof. Okay, we have these two lemmas now. The first one tells us that a map is bijective if and only if it's invertible. And the second one tells us that the composition of two maps is, the composition of two bijective maps is also bijective. As a consequence of lemma 2, actually, we also get for free that the inverse of F of G is G inverse of F inverse. So the way to take the inverse of a composition is to invert the symbols and then distribute the -1 exponent. I shouldn't say exponent, it's not really an exponent, the superscript. Okay, and this is enough to prove the main result, which is that this notion we defined before is an equivalence relation. So here's the proof. Let's do reflexivity first. Well, we want to show that X is equivalent to itself, or X is isomorphic to itself. So the identity map from X to itself is a bijection. Well, one way to see this is to just realize that, well, what does it do? It maps every element of X to itself, right? Obviously, it's going to be injective and surjective. The other way to see it is to realize that the identity map is a self-inverse. right? The identity map composed of itself is just the identity map. It does nothing. So that tells us that the identity map is invertible, and so lemma 1 implies that it's a bijection. Right? And so this, by definition, tells us that X is isomorphic to X. Okay, great. Let's do symmetry. So if X is isomorphic to Y, what we want to do, we want to show that Y is isomorphic to X. Well, if X is isomorphic to Y, then there is a bijection F that sends X to Y. Now, by lemma 1, there is an inverse, F inverse, from Y to X, which is again a bijection. How do we know it's a bijection? Well, because F is an inverse for F inverse. So lemma 1 again tells us that F inverse is a bijection. Okay, but now we've established a bijection between Y and X in the other direction. That tells us that Y is isomorphic to X. So there's the symmetry. We have that if X is isomorphic to Y, then Y is isomorphic to X. And then finally, the last piece is the transitivity. So if X is isomorphic to Y and Y is isomorphic to Z, then there are bijections F from X to Y and G from Y to Z. Okay, this is the definition of sets being isomorphic that we defined. Okay, well, by lemma 2, the composition G of F from X to Z is also a bijection. So we're assuming that X is isomorphic to Y and Y is isomorphic to Z. The definition of that is that there are bijections from X to Y and from Y to Z. If we compose those bijections, lemma 2 tells us that we get another bijection. And this time it's from X to Z. And so actually, this implies that X is isomorphic to Z. And that's the transitivity. And so it's the isomorphic notion we defined is an equivalence relation. Okay, great. So this is great. We now have a notion of when two sets are equivalent, and it's an equivalence relation as it should be. Now the question is, how do we classify all sets? So what sets belong to the equivalence class of X, and for some X, and which don't? So it turns out that we can answer this question with just one simple computation for the case of finite sets. I just need to give you one small definition. The order of a finite set x is the number of elements in the set. So we write these sort of absolute value vertical line symbols to mean the order of the set, and that'll be equal to n if there are n elements. Okay, so the classification of sets that we're looking for is given by the following theorem. If x and y are finite sets, with the order of x equal to the order of y, well then x and y are isomorphic. Okay, so the proof is actually very simple. Why don't we go ahead and write out some sketch of this. Let's let the order of x equal n. Let's make sure it's the same thing as y, like in the assumption. So pick some x in the set x and define a map f from x to y oh, sorry, I don't want to define it from x to y. I want to define it from x to the set. Here, let me write it down here. I want to define the map f to go from x to the set 1 through n. We want to define it by f of x is equal to 1. So this doesn't define the entire map, it just tells us where this one particular element x goes. Okay, so now let's remove x from the set. So there are now n minus 1 elements of x that have not yet been used. So we'll say assigned. Okay, so take another element. And we'll map it to 2, and so on. We'll keep doing this procedure until we eliminate all the elements in the set x. So this operation has to terminate because there's only finitely many elements in F. Okay, so the resulting map is a bijection since we've constructed it to be invertible, right? I sent x to 1 specifically. I sent the next element to 2 specifically, and so on. I can always just go right back. So this shows that the set x is isomorphic to a set of integers from 1 to n. Okay, so do the same for y. So do the same for y. This tells us we'll find that y is also isomorphic to 1 through n. And since this isomorphism symbol, this notion of equivalence that we defined, is transitive because it's an equivalence relation, that tells us that x must be equivalent to y, because x is equivalent to this set and that set is equivalent to y, and so x must be equivalent to y. And that completes the sketch of it anyway. Okay, so the answer to the question, what sets y are equivalent to a set x, is, well, it's all the sets y that have the same number of elements as x. At least this is the case for finite sets. Here's a question. If two sets x, y each have infinitely many elements, is it true that x is isomorphic to y? So if you extend this notion of the order to infinite sets, you just say that the order is infinite for both of them. Are these things equivalent? It turns out the answer is a resounding no. So this is a really wonderful topic that I encourage you guys to explore. You'll find that there are different sizes of infinity when you get into this, which is just a wild concept to me. But it makes sense. There aren't as many integers as there are as real numbers, for example. But on the other hand, what's less intuitive is that there is, in some sense, the same number of rational numbers as there are integers, even though the integers are strictly contained in the rational numbers. So this is just, such as the notion of infinity. So there's a mathematician, or there was a mathematician by the name George Cantor. George Cantor, who's famous for studying this area. And I really recommend this book called Mystery of the Aleph. I think this is by Mir Axel. I don't know how to pronounce his last name. But I really highly suggest this book to learn about George Cantor's remarkable struggle. Okay, so we won't touch on this topic of infinite sets because I don't think we will really need to for this representation theory of finite groups. But if it comes up, we'll discuss it. But what's next? So there isn't a whole lot that you can really do with the idea of a set. After all, it's nothing more than a collection of things. So next what we'll do is we'll give sets a little more structure in the form of a binary operation. So that's we're going to define what's called a group, which is just a set G plus a map. I'll denote it by this little dot here, which takes two elements of G and gives you another element of G. And it'll have to satisfy a few axioms. But we'll define this notion of a group, and we'll watch as suddenly the world of applicability just expands dramatically. At the same time, what we'll see is that the tools that we develop today make another appearance. So one aspect of saying whether two groups are in some sense equivalent to each other is to preserve the structure of the set. And so when you construct a map between two groups that signifies an equivalence, you'll want it to be bijective, right? Because the bijectivity preserves the structure of the set. But it'll turn out that we want just a little more structure on our map in order to say that two groups are isomorphic to each other. And we'll want that extra structure because we want to preserve this binary operation here. Okay, but we'll talk about that next time. So see you soon.